You are falling toward Earth. A thick, gray-yellow atmosphere wraps around the entire planet, while scattered volcanic islands rise from dark green acidic oceans. This is still not the blue planet you know. This is the Primordial Earth, 4 billion years ago. You plunge into the atmosphere, fierce winds whistling across your visor. But compared with your last journey through the Archean, this experience is far more pleasant. Fine sulfide particles drift through the air, released by the frequent volcanic eruptions raging across the Archean Earth. Below, the dark ocean resembles an emerald covered in dust. The sea wind sweeps across it, breaking the crests of the waves apart before they close again. You set foot on this planet once again. Beneath you lies black basalt, still holding the lingering warmth of magma, while the enormous moon hangs overhead like a giant bathroom heat lamp, casting an eerie green glow across the ocean. You raise a hand to remove your visor, then suddenly remember that there is not a trace of oxygen in the atmosphere. Instead, the air is filled with hydrogen sulfide that smells like rotten eggs. Take one breath, and you become a takeout meal for the microbes. But to these anaerobic organisms, oxygen is the deadly poison that kills on contact. You look up at the sun and find it far dimmer than it is today. In theory, sunlight this week should have frozen the oceans solid. Yet carbon dioxide and methane released by volcanoes wrap the surface like a thick blanket, trapping the heat below. The sun may not be ready yet, but Earth has already preserved an unfrozen ocean for life. You continue along the coast. High tides carry iron, sulfur, and volcanic minerals into pools between the rocks, while low tides concentrate them together. Lightning repeatedly tears apart molecules in the atmosphere as seawater cycles through heating, cooling, and evaporation. The entire coastline is like an unattended laboratory, with Earth using immense stretches of time to select the raw materials for life. You lean against a rock and take a short nap. When you open your eyes again, 400 million years have passed. You leap from the cliff and plunge several thousand meters down toward a hydrothermal vent on the ocean floor. It is billowing dense black plumes of sulfides, like a black chimney rising from the seabed, while 300 degrees Celsius fluids collide with the cold seawater and churn up clouds of white mist. The rocks around the vent are covered with transparent specks no larger than pinheads. These deep-sea hydrothermal vents are the earliest cradle of life on Earth. You drift with the currents for 100 million years and arrive in shallow water where sunlight can finally reach. The rocks beneath you are covered by blue-green microbial mats, releasing tiny bubbles like a glass of soda. Yet each bubble rises only a few meters before the seawater eats it. These are photosynthetic bacteria performing an oxygenic photosynthesis, using sunlight to sustain themselves. Meanwhile, the ocean is filled with reduced ferrous ions. Even if a trace of oxygen forms, it immediately reacts with the iron and sinks as sediment, never reaching the surface. Even more remarkably, these microbial mats secrete mucus every day, trapping mud and sand from the seawater on their surfaces. Older colonies are buried, while new ones climb back to the top to bask in the sunlight. Over time, the flat seafloor rises into layer upon layer of stone mounds. These are stromatolites. For the first time, life is no longer merely living on Earth. It is building new landscapes with its own hands. The resources in the shallow seas soon become too scarce to share. Some cyanobacteria begin trying to use the seemingly endless supply of seawater directly. With energy from sunlight, they split water molecules, keep the energy for themselves, and release oxygen as waste. This new ability allows them to spread rapidly. It also marks the first time a gas that has never ruled Earth begins to be produced in enormous quantities. 300 million years later, you discover large amounts of dark red sand across the shallow seafloor. This is ferric iron, formed when oxygen reacts with iron. By now, cyanobacteria have finally unlocked oxygenic photosynthesis. The oxygen they release continuously combines with iron in the seawater and settles to the ocean floor layer by layer. After accumulating for hundreds of millions of years, these deposits become banded iron formations, holding 70% of the world's iron reserves. The kitchen knives in your home and the steel panels of your car are, in essence, a fortune built from the bubbles of these tiny organisms. Oxygen continues to enter the ocean. The ferrous ions once dissolved in the water steadily turn into rust and sink to the seafloor. Dark red sediments accumulate layer after layer, while the amount of iron left to consume oxygen grows smaller. The dusty, dark green ocean finally begins to lose its original color. For the first time, life has changed the chemical composition of an entire ocean. You return to the surface, where the next 400 million years are extremely turbulent. The land beneath you collides like pieces of a building set, eventually sticking together into one enormous mass. Around 3.1 billion years ago, Valbora, Earth's first proposed supercontinent, takes shape. By 2.8 billion years ago, it has already begun to break apart. New shallow seas form along the broken edges. Standing at the edge of this vast landmass, you look down and see that land now covers 1/10 of Earth's surface for the first time. Broad, shallow seas spread around its edges, giving cyanobacteria all the territory they need to expand. You discover that cyanobacteria quickly cover the newly formed shallow seas. During the day, vast microbial mats release oxygen together, creating temporary oxygen-rich zones in some enclosed bays for the first time. At night, rocks, volcanic gases, and microbes rapidly consume it all again. These oxygen oases are like scattered islands in an anoxic world. They appear and disappear, yet with each passing year, they become harder to erase completely. One afternoon, 300 million years later, you see a chain of bubbles drifting gently out of the ocean. This time, the seawater does not swallow them. You know that the reduced iron in the ocean has finally been exhausted. During the Great Oxidation Event, which begins 2.5 billion years ago, the oxygen released by cyanobacteria starts pouring into the atmosphere continuously and on a massive scale. The entry ticket for complex life has quietly been placed into its hand. But to the anaerobic organisms now spread across the planet, this oxygen is a poison that kills on contact. They will be forced to retreat into oxygen-free refuges in the deep ocean and underground, surrendering the vast surface and shallow seas to the new forms of life about to appear. And when that time comes, what kind of world will be waiting for you?